Today we discuss about microring resonator uh, passive characteristics, because microring resonators can be designed for various active functionalities. So, first we need to know what is its passive characteristics and what all figure of merits we need to learn, that we will be discussing first, and then we will give some practical device design and couple of experimental results, that how it is related to theory, that we will be discussing today. So, we have already introduced ring resonator, the theory already developed. So, if you have a bus waveguide and coupled ring waveguide is there, and there are input field, output field annotated, and inside field we annotate with two different components, AI and A naught. So, based on the analysis, based on the steady state condition, we actually defined two parameter. One is field enhancement factor inside the cavity ring resonator, that is nothing but EI by BI. BI is the field in the field amplitude in the bus waveguide, and AI is the field amplitude in the inside the ring. It could be A naught also, that does not matter, they are related, A naught and AI related through this equation. Okay. This is actually called field enhancement factor inside the cavity, and then this one we derived, that is the transmission characteristics, B out, BO to BI, what is the transfer function for the microring resonators. So, in this derivation we have used this directional coupler transfer matrix. We define it as a MDC, that means matrix for transfer matrix for directional coupler, we define like that. And then we have already defined one more parameter called loss factor, which is actually A equal to e to the power minus alpha L, where alpha is the loss coefficient. And then we have also derived that these two things, delta nu FSR and so called free spectral range. We will discuss that a little while later, that is nothing but C over NGL, where Ng is the group index, and that can be again converted into delta lambda FSR, because we know nu and lambda is related by this. So, delta nu can be written as minus C by lambda square delta lambda. So, once we know delta nu, we can actually relate delta lambda FSR also, where group index of the waveguide we define like n effective plus omega dn effective by d omega. Of course, this can be also converted into lambda function, Ng equal to n effective. If we convert omega to lambda, then it will be written as dn effective by d lambda. That is one way. And then this is amplitude field enhancement, and that is the transfer function for the amplitude in the all pass configuration. And if we take just complex conjugate and multiply, then we will get this intensity enhancement inside the cavity. That means, it measures the power, how much power it is amplified or can be stored, is stored inside the microring resonator, that can be expressed in this one. Just you take complex conjugate and multiply, then you get the, we call it as a power transfer function. Similarly, for transmission we will be having this TR star. So, we get power transmission coefficient, transmission parameter function, we can define like that. You know, in this process, in this derivation, we have just assumed this R equal to R star, that is actually consider R, and directional coupler is lossless, R square plus T square equal to 1, but ring, inside ring, whatever loss is there, that has been attributed to A, that is the loss factor. So, this much we have learned in the previous lecture, previous class. So, we also learned that in this function, if you say this is the field inside or power inside, that actually gives the value, how much power is inside from this expression, and if you carefully look into it, then we can identify that in the denominator you have one factor called cos beta L, right. So, this cos beta L can vary from -1 to +1, right. So, when cos beta L equal to +1, that means denominator is minimum, and cos beta L equal to -1, then denominator is maximum. So, maximum to minima we can have. So, in that case maximum power storage, cavity power will be possible when cos beta L equal to +1. That means denominator equal to minimum, denominator of course is minimum. If it is minimum, then only you can get overall maximum. So, in that case, if cos beta L is equal to 1, that means beta L has to be integer multiple of 2 pi. M is the integer, m 0, 1, 2, 3, 4, so on. So, in this case it can start from 1. So, in that case I can say that the power inside the cavity can be quantified by this expression when cos beta L equal to 1. That means, it will be 1 minus r a square, and numerator is a square multiplied by 1 minus r square. So, that is the thing, the resonance, we call it as a resonance condition, resonances, and that resonances can be expressed. Beta, we know beta has a relationship with omega by c n effective. So, beta can be converted into omega. So, in that case we can find frequency is discrete frequency solutions which can give you higher power storage inside the cavity, and that particular corresponding frequencies will be called as a resonance frequencies. So, at resonance frequencies, the field or the power inside the cavity is quantified by this one. At the same time, when we put beta L equal to 2 m pi, transmission characteristics here also cos beta L equal to 1, cos beta L equal to 1. So, that we will call that at resonance what is the transmission power transmission characteristics, we can quantify it. So, r minus a whole square 1 minus r a. So, that is straightforward, and as I mentioned that beta can be represented as omega by c n effective and multiplied by L, that is written, that is actual 2 m pi. From here, for different m values I can get a discrete solution for omega, that is omega m, we can call it as a mth order resonance angular frequency. Of course, omega to linear frequency we can relate like this, omega equal to 2 pi nu. So, we can get, instead of omega m, we can actually derive linear frequency, and also we can convert also omega relationship with the lambda, omega equal to 2 pi c by lambda. So, in terms of lambda we can find the wavelength corresponding to resonance order m. So, mth order resonance wavelength we can define that thing. Okay. This is all about the theoretical aspects, right. So, now whatever we have discussed, that considering this nu f Hesher, delta nu f Hesher free spectral range, and in terms of lambda, in terms of frequency we have expressed this one also, and group index whatever we have written here we repeat it here for completeness. Okay. So, we can get, because this is easy to get once we know this relationship. From this relationship we have derived that if we go for successive resonances mth to mth plus 1th resonances and their separation, if we find the frequency separation, that will be called as a free spectral range. So, that the frequency separation between successive resonances, and this is the wavelength separation between successive resonant wavelengths, and in that case we need to introduce this group index, that is standard for, because whenever we are considering resonance or wavelength dependent things, that time group index actually matters. So, we actually summarize here about all the important equations. So, delta nu f Hesher given here, group index given here, and then power inside the cavity can be quantified by Hesher, that means A I by V I, that is the ample field enhancement, square of that actually power enhancement inside the cavity. This is the power transfer function, maximum power storage at resonance beta L equal to 2 m pi, resonance whatever discussed so far repeated here. and beta omega relationship, beta lambda relationship. So, all these we will be needing to discuss about the overall spectral characteristics and the figure of merits of a microring resonator. All right. So, we consider a waveguide dimension of 500 nanometer in silicon on insulator. You know that if it is a substrate and this is your silicon substrate and then this is your oxide Si2 box, okay, this is the box, and then the top you can have your waveguide structure, okay, and this waveguide structure W equal to this one equal to 500 nanometer width and this height equal to H equal to 222 nanometer here, consider W equal to this one, and small h, that is the slab. Example of SOI waveguide we consider, that is actually 90 nanometer. Using this waveguide we constructed this ring and bus waveguides, and if we choose a suitable length here, coupling length, then we can actually consider how much it will be self coupled and how much it will be cross coupled. Self coupling parameter is R and cross is T. Okay. So, R value in this case we have considered, we have adjusted this bus waveguide and ring such that the R coefficient here, that means self coupling, R is the self coupling. Self coupling means whatever you are get in a directional coupler, whatever you get in the bar port, that is actually responsible because of the R. So, that value is almost, that means almost 98% amplitude electric field strength is appear in the output, and L, that means total perimeter length, it is actually 100, it is basically something like the ring type configuration. You can consider 100 micrometer is the bending radius. So, 100 micrometer bending radius, it is considered sufficiently large, so that bend induced loss is as minimum as possible, such that we can get A, this loss factor, whatever we have defined here, loss factor, this one A equal to e to the power minus alpha L, loss factor it should be close to 99%. So, this alpha value should be as minimum as possible, so that A will be close to 1. So, alpha tends to 0, then A tends to 1. Alpha is very large, then A will be dropping. So, that is the information. So, alpha, even if it is for 1 dB per centimeter loss, we can get that one round trip you will lose maybe less than, hardly about 1% or less than 1% power you will be losing. Okay. So, for A, if we consider like this, and input power here P input is nothing but Bi square we consider accordingly, according to our convention so far, is 1 milliwatt if we consider, then we can plot both DR and SR. That means, with respect to 1 milliwatt, how much I am getting in the throughput and how much I am getting in the inside the cavity, and that I will be using with wavelength as a function of wavelength. This beta I will be converting, expressing this beta here, beta L will be writing as 2 pi by lambda times n effective, corresponding lambda effective index I will be computing, and L I will be using. And then if I tune this lambda value, okay, whenever this beta L will be integer multiple of 2 pi, I can say that this will be maxima and this will be minimum. So, exactly whatever we got, this blue curve here you see, at certain wavelength if you see, transmission is dropping, transmission is dropping, transmission is dropping, certain wavelength. They are actually resonance frequency. At that particular frequency, if you calculate SR, you see the power or intensity is increasing here. And in this y axis if you see, this is actually, we called it dBm. You know what is dBm? dBm is actually you have to consider P out by P in log of 10 to the base 10, that is actually the gain or loss in dB. Okay. whatever P out you express in unit and P input you express in unit, that if it is what, it is what, then you can get the what cancel, then you can get whatever gain you get. So, for example, you are getting, for example, SR maybe 10 dB if you are getting, that means if you are inside SR output will be about 10, right, and then 100 and this one may be 10, input is 10, P input is 10, that means it will be 10. So, in that case 10 dB will be the inside, more gain will be there inside, and correspondingly if you will get P out by P input negative, that means it will be dropping. Okay. But sometimes it is considered, suppose milliwatt power you can express in dBm. How it is that? Suppose whatever power you launched or available to you, you just take log of that power in milliwatt, whatever power you are getting, power in milliwatt, you take log to the base 10 and multiply 10. Whatever value you get, that will be called as a dBm. That means, if I consider my input power is 1 milliwatt, input power is 1 milliwatt, output power whatever value is there, P output log of 10 to the base 10, that will be actually your output y axis I am plotting, this normalized power in dBm. If input is 1 milliwatt and then whatever value I am getting at the output according to this one, because Bi square I will be getting 1 milliwatt, then I can calculate Ai square, putting all these value I can calculate Ai square, Bi square if I put here Bi square, that means it is 1 watt, that means Ai square I will be getting 1 milliwatt, corresponding Ai square whatever in milliwatt I will be representing. That milliwatt, if you just get that milliwatt, log of that whatever output you are getting and 10, that is actually plotted in y axis. So, in dB scale actually the you can actually see the signal to noise very clearly, that is why normally power density or amplitude ratio normally we represent in dB scale. Okay. So, here you see if I launch 1 milliwatt power, 1 milliwatt means, that means I can say that 1 milliwatt if you are expressing in dBm, normally you can get log of to the base 10 1 milliwatt, right, 1 milliwatt by 1 milliwatt 10. So, that means log 10 1, that means actually 0, 10 times 0. So, that will be called as a 0 dBm. So, we can say that 1 milliwatt corresponding to 0 dBm. Similarly, if we have a 10 milliwatt, then we 10 milliwatt means you will be at 10 log 10. So, that will be 10 milliwatt, that will be 10 milliwatt, that will be 10 dBm. Okay. So, similarly, you can have 100 milliwatt, that will be 20 dBm and so on. So, 1000 milliwatt, that means 1 watt, that means 30 dBm. So, milliwatt to dBm, that unit conversion you can actually express. So, my point is that if I consider at the input it is actually equal to 1 milliwatt you are launching in the bus waveguide, then inside if you just follow SR, that is reaching close to just this is 10 dBm. So, that will be actually about 18 dBm or something like that. So, that means inside field it is enhanced at resonance. Power inside the cavity, that is now it is increased many folds, close to 20 dBm. That means 20 dBm means how much? That is about 100 milliwatt. So, that means you are launching here 1 milliwatt and it is passing, but inside in steady state it is storing 100 milliwatt power flowing inside, all the time 100 milliwatt it is flowing, okay, if it is 20 dBm. So, that is the beauty of a microring resonator. You can store energy at resonance. When resonance wavelength reached, you can actually enhance the power strength inside you can store the energy inside the ring, and in the transmission you see that at that particular wavelength that much energy is dropped here. How much? Exactly not 20 dBm, because that actually follow this rule according to this transfer function. So, you will see it will reach up to this level. So, it will follow exactly at resonance. If you know the R value, A value, 1 minus R A, whatever value comes, that you take log scale. So, you get this one. Another resonance wavelength. So, all the resonance you see inside field is enhancing, and in the transmission it is dropping, perfectly it is dropping, this one dropping, 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 and it is enhancing inside. So, red curve corresponding to SR, blue curve corresponding to TR. So, when transmission drops at that particular wavelength, that is the resonant wavelength, at that particular resonance inside the ring, the power density increases, power level increases. So, that is the beauty of a microring resonator, that is why it is called resonator. Okay. Now, here we showed that if inside the loss factor is decreased, loss factor is, that means A is decreased. A is decreased means typically when A dropped, that means round tip A drops, that means alpha value is actually increasing, right. When alpha value is increasing, that means A equal to 1 by e to the power alpha L, right. So, when alpha value increases, in that case A will be dropping. So, that means loss, waveguide propagation loss increases, I will be getting this type of characteristics. You see, when loss increases inside the cavity, you see the storage here it is much higher, and here red curve if you see it is slightly dropped. But at the same time, depending on this value, because A is increased, here also the value will be there for a given R. R value always we have mentioned this one, this we have used R, that is self coupling coefficient here, that is R. So, in that case you see this storage will be dropped and extinction will be more here. Here in the resonance, in the transmission, if you see blue curve is the TR. So, it will be, it is going more and more extinguished. So, throughput is reduced at that resonant wavelength. Okay. At the same time, your storage power throughput reduced does not mean that your storage power will be inside whatever stored SR, that will be increased, because this is reduced, the throughput is reduced because of the A loss in the waveguide. So, loss is there, loss, if loss is there, inside power also cannot be increased too high. So, that is what it is evident here. Okay. So, this is how we can just express, we can just plot directly this expression we can plot as a function of omega, SR and TR as a function of omega, TR, where TR will be minimum, there SR will be maximum. So, TR minimum means it is resonant, and at resonance energy will be stored, power will be stored inside the cavity, and inside the cavity energy will be stored more if loss in the waveguide in the ring if it is less. Okay. So, this is very important, and in this case if you see FSR, if you try to say FSR means free spectral range, that means one resonant wavelength to another resonant wavelength, what is the separation. Okay. This to this separation if I see, I will be getting 1.134 nanometer for all these parameter. So, for example, here 1541.5 nanometer one resonant is there, and if you go for next resonance 1542.5 plus something somewhere here. So, if you see the difference separation, the difference in resonant wavelength, successive resonant wavelength, that is what your delta lambda FSR, and that is actually this side is 1.138, slightly higher, because you see in delta lambda FSR it is proportional to lambda square. More the lambda, higher lambda value if you are trying to measure, FSR will be more. So, this is higher, you are going towards higher wavelength. So, that is why delta lambda FSR, that means FSR will be more, and this side is you are going for shorter wavelength, that is why FSR will be lower. Okay. However, if you see the in case of free spectral range in terms of hertz frequency, in that case C by NGL, that is not a frequency dependent. So, that actually depends on group index. So, as a function of group index, if group index is frequency dependent, then only it will be, you will be seeing that delta new FSR will be varying resonance to resonance. Otherwise, they will be remaining constant as long as Ng is constant. So, that means you see relatively free spectral range in terms of frequency, it is more regular, because it does not depend on frequency, but in terms of lambda, if you try to see free spectral range, then you can see it is square proportional to the square of the wavelength. That is what it is reflected also here, the separation. Whatever from the simulation, whatever we are getting, we just calculated exactly that way, and it actually matches this formula also. So, this is free spectral range. So, all this figure of merits actually very important if you are planning to use such microring resonator for various applications. Okay. Now, another one, again your P input is 1 milliwatt if you are considering, as I mentioned that if you are just increasing loss 1 dB, 2 dB, 3 dB, then loss factor actually if you are increasing loss, then loss factor will be actually reducing, because that is again A equal to 1 by e to the power alpha L. If alpha it is in nipper it is shown, but you can convert nipper to decibel, we have discussed how to convert that. So, if alpha is increasing, A will be dropping, A will be dropping. So, if A drops, that means loss is high. A drops means that means round trip, one round trip, how much it is coming. Okay. It is reducing means loss is increased. A is reducing means loss is increased. So, when loss is increased, you see the peak, this is actually SR we plot again, normalized cavity power. So, when we plot SR for a BI equal to 1 milliwatt, BI square equal to 1 milliwatt, then whatever power I get, that is actually power inside the cavity if I plot. So, as loss increases, it drops, the power will be dropping. That is what, if it is 1 dB per centimeter or 2 dB per centimeter, 3 dB per centimeter, then loss will be. So, that means if you can fabricate your waveguide, loss is low, well designed, and technology is very good, so that you do not get much scattering losses etc. in the waveguide, then you can store more energy inside the microring resonator. Okay. So, at the same time if you see the transmission also it will be varying. Okay. So, when loss is actually increasing, you see when the extinction in the transmission, that can also be controlled depending on the loss factor. Okay. So, so far so good. Now, let us move on. So, we have almost discussed whatever things are required. Now, how to calculate 3 dB bandwidth analytically? We know that there are resonance wavelengths, certain wavelengths you see here according to this thing, this is the resonance wavelength, the energy inside how much it will be storing. Now, I want to know what is the 3 dB bandwidth. 3 dB bandwidth from maxima, if you come down 3 dB below, and then you see the width, spectral width of the resonance spectrum. This is the resonance spectrum. So, that 3 dB bandwidth, how to calculate analytically? We can numerically simulate this curve, and this curve, specifically this is very important. So, this one if I plot, I will be getting this one, and then I see okay, this is maxima, maxima is happening about 18 dB. 18 dBm. So, I come down 3 dBm about 15 dBm, then here I see that whatever this omega 1 and this lambda 1, and then this one if I plot, this one if I estimate, that will be your bandwidth, 3 dB bandwidth. But can we calculate that analytically? Okay. Analytically means can we express or can we derive an expression without simulating this? I can directly put some parameters, so that I can predict what is the 3 dB bandwidth of this resonance. Let us try that. Okay. Now, we just consider SR, amplitude field enhancement inside the cavity, AI by BI, BI is launching, AI inside field, that is expression we have derived, and this is the power enhancement inside. So, I know that if I am launching 1 milliwatt, then whatever value comes, that milliwatt will be inside at a resonance, that is the maximum. Once again I repeat that frequency, resonance frequencies can be expressed to pi times integer. Okay. Now, what we do? Let us assume that beta m is a resonance corresponding to resonance. Beta m means this one. This one, in that case, this cos beta L term will become 1, right. Now, if cos beta L term if it is 1, then this will be 2 m pi, cos beta is there or not, that depends on what is the value of beta L. If beta L equal to 2 m pi, this term we do not need to use. Now, if this beta L is slightly higher, corresponding instead of beta m L, you have just adding additional delta beta with beta m and then L. This delta beta, how you can additionally include? You tune your frequency a bit from the resonance wavelength. If you tune your resonance wavelength a bit, then you can see that your beta L, instead of 2 m pi, it will be slightly increased. So, in that case you will be writing something like that, cos 2 m pi plus 2 m pi plus delta beta L. This will be 2 m pi plus delta beta L, because you have detuned this 2 m pi corresponding to frequency, mth frequency. Now, you frequency little bit detuned, so you supposed to get a little bit of delta beta change, because omega is there. So, in that case I can write this one exactly equal to delta beta L, because 2 pi plus theta, cos 2 pi plus theta is cos theta. So, we can write that one. If that happens, I can find that certain beta change, whatever happening, that we define as x, okay, and this delta beta is changed such that SR value, whatever you supposed to get at resonance for beta m equal to 2 m pi, you detune delta beta, so that your maximum strength here, according to our this formula, this thing, this is your SR max at resonance. Now, if this is your resonance frequency here, lambda m wavelength. Now, you detune a frequency bit right hand side, then once you detune such that your maxima become half, 50%. Whatever you supposed to get at resonance, if you detune a bit, then your maximum will be dropped to half. So, I assume that delta beta we need to find out, and delta beta if we find, I know what is the relationship between beta and omega, and delta beta we will be able to find. Then we can find whatever the 3 dB bandwidth, that is the whole idea. So, delta beta L x I am just considering, delta beta L equal to x. So, that means I can write, you just note down, I can write a square 1 minus r square, that is numerator that I have written here, and this one 1 r square plus a square minus 2 r a, instead of completely removing cos delta beta L in resonance, I have detuned a bit, that detuning value is delta beta L equal to x, I just put down here x, and it has been changed, detuned such that the maxima is supposed to get this one, because of detuning maxima, your power inside the cavity will drop to half, exactly half of that. Now, from this expression our intention is that can we try to find out x. Once we know x value, then we can find out delta beta. Once we know delta beta, then we can find how much frequency is detuned from resonance, then you can get at that particular frequency the maxima will drop to half. Field strength or power inside the cavity will be half at that particular frequency. So, our intention is to find out now x from this expression. So, if you just carefully see numerator both sides same. So, denominator will be, you can compare denominator 1 plus r square a square minus 2 r a cos x, and this is 2 times 1 minus r a whole square, that can be expanded as it is a minus b square, a square plus b square minus 2 a b we have written, right. So, if you just from this we can express cos x in terms of r a. We have assumed that the values of r a everything are known from some other sources, either by numerical simulation or by calculations, we know that. So, we can express the cos x, we can represent like this, you can represent like this, and we can little bit simplify like in this form 1 minus 1 by half 1 minus r square. Okay. So, cos x I can define like that. Now, you know this cos x value actually is not very large, it is just a little bit detuned from the resonance wavelength, so that you get a delta beta and then you get x. So, it is not, you need not to change this delta beta very large value. So, in that case this cos x you can just express as 1 minus half x square, cos x equal to 1 minus approximately equal to, you can write 1 minus half x square, then again you could write 1 plus all the Taylor series you can expand, right. So, I can take first 2 terms. So, if I do so, I have written that cos x equal to this one, this I have written half x, and you have this one right hand side, you see they are identical, 1 minus something half and 1 minus half something. So, that means x square equal to this one. So, that means x equal to 1 minus R A square root of R A. So, that is very interesting, x equal to delta beta L. So, delta beta L equal to this one. I know now if my delta beta L exactly match to R and A known depending on the waveguide parameter, what is the loss factor and what is the self coupling coefficient for the directional coupler, all these are known, then I know what is the delta beta L required, so that your power inside the cavity drops to half what would you expect at resonance. At resonance you expect maximum storage. So, if we detune delta beta L, so things will be dropped to half. Now, you do one more thing, we know that beta equal to this one. So, we try to find out, you just make a differentiation delta beta L, L you are multiplying both side, that means beta L equal to omega c by n effective. Now, I do derivative with respect to omega, for example, delta beta L, that means L by c I can write, and n effective just you do delta beta equal to 1 by c, you just put omega, if you just make derivative then it will be delta omega, n effective I just write delta omega, for example, d beta by d omega, n effective, and then you can write omega d n effective by d omega, right, and this delta omega I can take this side delta omega, and if I multiply here I can multiply here L by c. So, that is how we are getting here, and this one we know that this is Ng group index. So, that means Ng L divided by c, Ng L divided by c delta omega. So, I can write delta beta L equal to this one, delta beta times L equal to Ng times L by c into delta omega. Okay. So, I can just put here, this is the delta beta L expression, and then I can find out what about the delta omega. So, from here I can find delta omega. So, now you see I can say that resonance spectrum is like this, and this is your some omega m resonance mth resonance frequency. Now, you move delta omega this side, then it will drop to half. So, I get this value is this one. So, if I want to find out FWHM full width at half maxima, then we have to multiply delta omega times 2. So, FWHM will be 2 times you have to multiply with this. So, accordingly I get delta nu, because delta omega I can convert 2 pi. So, okay, this one I can write delta omega equal to 2 pi times delta nu. So, 2 pi has to be divided this side, that is we have written, and then we do FWHM 2 times delta nu, that is I represent as capital delta nu. So, capital delta nu I can get here. So, FWHM, that means 3 dB bandwidth, 3 dB means 50% down. So, how to calculate 3 dB bandwidth? If we know R value, directional coupler, and A waveguide loss, A value here, and if I know the perimeter length, if I know the group index, of course, C and pi are constants, then I can find how much 3 dB bandwidth will be there for the resonance. Okay. So, this is interesting. So, you can find out from the waveguide parameters, design parameters, you can design a ring resonator to expect certain full width at half maxima. If you just increase, for example, L value, the volume of the ring resonator, if you are increasing, then delta nu will be, the full width half maxima will be narrowing down. And if you, for example, if you are just somehow reducing L, then it will be broadened. So, if your resonator perimeter length is shorter micro ring resonator, then your bandwidth, that means FWHM will be broader. And apart from that, for example, you just consider A is the waveguide loss. If waveguide loss is increased, then you see here square root of RA. So, in that case, if it is increased, normally loss is increased, then this will be reduced and this will be also reduced. So, ultimately delta nu we will see that when loss is increased, delta nu will be increasing. okay, full width half maxima. Whatever the result you can just find out depending on the, for example, if you just consider R A equal to 1 for example, somehow if you can manage to get R A equal to 1, never possible, because R A is also less than 1, A is also less than 1. So, R A cannot be 1. If only R A equal to 1, then you can say that delta nu will be 0. That means perfect line you delta function you will be getting. Perfect delta function at exactly that particular frequency you will be seeing the resonance. So, normally that is never possible, that is why your full width half maxima will be will have some width, bandwidth. Okay, practical device will have some kind of resonance bandwidth. That is the take home message. Okay. Now, how to calculate Q value of the resonator? So, we have learned that it is a resonator. So, resonator means, you know, in electrical circuit also, resonator means it can store some energy, right. So, if it can store energy, we can quantify a figure of merit called quality factor, Q value. The Q value actually defines how much capacity of storing energy at resonance. So, Q value we introduce just to justify how good is the resonator. So, higher the Q value means the resonator has a capacity to store more energy. Okay. So, that is actually how we define that. In principle, normally we consider that Q value is the, let us concentrate on this. So, we have already defined that delta nu in terms of frequency, full width half maxima. This is the expression we have derived, and if you convert into delta lambda, you know C always you C by lambda equal to nu. So, delta nu equal to minus C by lambda square. So, delta lambda. So, I can write delta lambda r square by is the resonance wavelength we have written. And Q value, as I mentioned, we concentrated on this, that is defined by 2 pi times. So, that is just for scaling factor we use. Ultimately, this ratio matters, energy stored by energy loss per cycle. Per cycle means at resonance frequency, the time period, how much time it takes to oscillate. So, time period is corresponding to resonance frequency, that is called cycle. So, per cycle, that means that is the time period. Normally, if you know nu is the frequency, then normally nu equal to 1 by t, t is the time period. So, within that time, for one cycle of oscillation at resonant frequency, how much energy getting lost and how much energy stored inside the cavity. If you take this ratio and multiply by 2 pi, that actually measures the quality factor. Ultimately, energy stored. Energy stored, you are taking ratio with the how much loss, and how much loss is happening, that loss is certain time we are considering, that is the per cycle. Per cycle how much energy is getting lost. So, this actually we define as a Q value. We just keep in mind, we will come to that point later after understanding this thing. Let us consider that inside the cavity EC amount energy is stored, total energy stored inside the cavity is EC. Now, suppose your this input you just cut, input whatever the continuous wave laser was there at a resonance and energy was stored and something you are getting out, you consider that okay, this is suddenly stopped, then what would happen? The stored energy inside the ring, they will start losing because of the loss and also coupling to the bus waveguide again. So, slowly it will start losing. If this EC is the energy and we consider EC is the cavity energy as a function of time at instant of time, once you cut it, the energy will start losing, right, inside the cavity. So, that can be a time dependent, and that time dependent energy loss, that means energy loss per unit time can be written as EC by tau c, where this tau c can be expressed as a cavity lifetime. That means, if you solve this expression, you get this expression. At t equal to 0, when you are cutting down, that time if your EC0 was the energy, total cavity energy in steady state. Now, whenever you are cutting your input, then it exponentially decays. Whatever energy stored inside the ring, that will be exponentially decaying, and at t equal to tau c, that energy will drop to 1 by E. That is why it is called cavity lifetime. So, even if you can imagine, if you are considering electromagnetic wave, light, you consider one photon is inside, and you can try to understand how long that photon will survive in that cavity. So, that is actually characteristically that in tau c, we can say that within tau c that photon will be lost. Basically, the classically it is 1 by E we say, that is our lifetime. It will be slowly to decaying, this energy stored inside. In steady state, whenever continuously laser was on for resonant wavelength, the energy was stored, and that energy is much higher than whatever you are, that power is much higher than circulating power, much higher than whatever you are launching, because of the storage capacity of the resonator. Okay. So, in that case, what you have? You will be getting, if you cut that one, slowly it will be lost, and that lost energy, lifetime is tau c. So, is this one. Now, I can say that stored energy is EC, I have written here, stored energy, and then we are writing here that energy loss per cycle, per unit time energy loss is dEc by dt. We can say that is EC by tau c we have written, and per cycle is time period I said. Okay. So, Q value can be expressed like this. In that case, what we get? Q equal to 2 pi EC by dEc by dC, this one I am writing EC by tau c, then EC cancel, and 2 pi by tau equal to, we can write 2 pi and 1 by t equal to nu r resonance frequency. I have set nu r equal to 1 by t time cycle. So, 2 pi nu r and dEc by dt equal to EC by tau c, EC cancel. So, 1 by tau c, that means this one. So, Q will be 2 pi nu r tau c. So, if we know this tau c, then you will be able to find out the Q value. That means, what is the lifetime in the cavity? So, longer it can stay any photon inside the cavity, the Q value is higher. So, it is clearly it can be understood that Q value depends on how long energy it can hold inside the resonator when your source is cut. So, longer the lifetime, your Q value is with more. Now, what we can consider, approximate the resonance as a Lorentzian shape. So, normally Lorentzian shape you know that around this one. So, normally 1 over nu minus nu naught square plus some constant will be there. So, if some frequency, if some spectral density, if you are considering I nu is proportional to this one, this is actually Lorentzian shape. And you know from Fourier analysis etc., we know that if any spectrum is Lorentzian shape, we can consider very good quality ring resonator. The spectral nature is almost looking like a Lorentzian, and in case of Lorentzian, the decay time constant and full width half maximum is related with this expression. So, basically tau c equal to 1 by delta omega c, angular bandwidth, angular frequency bandwidth 2 pi by 2 pi delta nu we have written, right. So, tau c we know this one, we can put this tau c expression here, 2 pi will be cancelled, nu r will be there and denominator will be delta nu r. So, that means Q value will be this one, resonant frequency divided by full width half maxima frequency bandwidth, 3 dB bandwidth, and nu r can be scaled to omega r 2 pi u multiply omega r 2 pi u multiply delta omega, angular frequency bandwidth, and omega r can be scaled to lambda r and delta omega can be scaled to delta lambda. So, lambda r by delta lambda. So, if you know the resonance wavelength and if you know the FWHM 3 dB bandwidth, then you can find out what is the Q value. This is the easiest way of estimating Q value. I know that FWHM expression known, this expression known, and I know how to calculate my resonance wavelength, that is coming from beta L equal to 2 m pi. So, beta if I write omega by c n effective, L m equal to 2 m pi. So, I know resonance wavelength. So, mth order, which order of resonance wavelength we are considering we can take. So, once we know the resonance wavelength and once we know the expression, then we can find out the Q value. That is what it is written. The Q value, this one is the Q lambda r divided by delta lambda r if you are writing this one. You are just writing this one lambda r, this will be denominator and lambda r will be in the numerator. So, lambda r, this one divided by this one. So, I write like this, lambda r divided by 1 minus r a lambda r square divided by pi n g l r a. So, that is actually your Q value. So, then lambda r, 1 lambda r will be cancelled, denominator 1 by lambda r, 1 minus r a written, and pi n g l root over r a, that will be going to numerator. So, Q value we have expressed. So, here n g, that is the waveguide parameter we know, L perimeter length we know, R, that means the directional coupler characteristics, I know how much self coupling coefficient, A is the round trip loss, I know, and lambda r, I am considering the lambda r which resonant wavelength, I can find out that N effective L should be equal to m lambda m. So, mth order, if I know the which order of resonance I am considering and then resonance wavelength will be known, then I can find the Q value. So, at a particular wavelength, what is the Q value I can express very quickly. You see, Q value is proportional to length and inversely proportional to lambda r. You can express this Q, another one figure of merit called finesse. Finesse is, you have a resonance wavelength here and resonance wavelength here, this is the resonance wavelength, this is called FSR, free spectral range, this is called another FSR, and here you can get the 3 dB bandwidth. Now, this FSR and 3 dB bandwidth, if you take a ratio, that is called finesse. Finesse actually gives how good you can resolve the resonance wavelengths. That means, if one resonant wavelength, another resonant wavelength, this is the separation, and if you see that if the separation is like this, if the resonances are like this, that means this is your FWHM, this is your FWHM and this is your FSR, and this FSR is exactly equal to FWHM, then your finesse will be 1. That is a very bad resonator. So, finesse is high means delta nu FSR, FSR will be larger compared to the full width half maxima. That is another figure of merit, we call it finesse F, and we know delta nu FSR, this expression, and delta nu FSR here, this delta nu FSR and delta nu FWHM here, take ratio, you get this expression. So, if you know the waveguide parameters, ring resonator parameters, and you can design R value, you can design what is the, you know what is the waveguide loss, bending radius, you can control A value, then you can get the finesse. Then one more parameter is called, if you see delta nu FSR, just this one, if you just see one important thing, C by Ng L if you just consider, then you get 1 over tau RT. What is tau RT? Just express this one, this C by Ng by L, C by Ng equal to group velocity by L. C is the velocity of light, Ng is the group index. So, C by Ng equal to Vg, group velocity by L. So, in that case you can write 1 over L by Vg. L is what? L is the total perimeter of the ring divided by Vg, that means velocity of group velocity, how the information travelling, how the data travelling inside the ring, that is the velocity. So, L by Vg means total perimeter divided by velocity, that means how much time it takes for round trip travel. That round trip travel we can write 1 by tau RT. So, once we know free spectral range of a ring resonator, then I can find a data, a signal, how much it will take time to get a complete round trip inside the ring. So, this is another important information we need to know for a ring resonator when we will be designing, when we will be using this type of ring resonator to design different type of delay lines, filter characteristics, that time it would be helpful. So, these are the figure of merits, finesse, quality factor and FSR. For a particular design, particular applications, we can look for these 3 figure of merits, and depending on these 3 figure of merits, we can actually use them. Suppose certain application I need Q value is very high. So, we need to design accordingly L, we can expect R value, what is the R value required, what is the A value required. We can assume that the NG group index, that depends on the single mode waveguide design, and what is the group velocity, what is the core material refractive index, what is the cladding refractive index, all those depends on NG. That can be considered as a fixed. So, now we can design whatever the value of R, whatever the value of A, R and A basically. That means the DC directional coupler, how you are designing, and A, what is the loss in the waveguide, that actually responsible for storing more energy or less energy. But this R and T, they do not influence free spectral range. Free spectral range is C by NGL, that depends alone on group index as well as length. So, one resonance to another resonance in frequency domain, what is the separation? C by Ng in hertz, you can find out. Okay. So, this figure of merits are very important. Now, let us move on. Practical device design and experimental results. So, we know that what are the important parameter for a microring resonators and how to design that, and these are the figure of merits. One is the full width half maxima in frequency domain, in wavelength domain, and Q value at a particular resonance wavelength lambda r, and for a given perimeter I know finesse also I have derived starting from the your normal transfer matrix mechanisms, right. Only thing is that we ensure that this transfer matrix is known, R and T is known, A also known, and L is known. These are known parameters. Once you know those parameters, then you can quantify what are these values. Okay. Now, one more particular device you can think of. This is what you call that this bus waveguide and a ring. Bus waveguide couples 1:1, one input, one output. It is basically a directional coupler. One of the output you are just giving as a positive feedback, and you are getting like a oscillator or resonator. Okay. Electronically, positive feedback gives you in as an electronic oscillator, like op amp you can use as a oscillator if you give a positive feedback. Okay. So, you can have another type of device where you have one bus waveguide where you are launching light couples, a resonant wavelength can store here. If you bring another one bus waveguide in the top, then the resonant wavelength which is stored here, that can be tapped through this bus waveguide again by another coupling parameter, so called R2T2. This one can be considered as this DC can be characterized with R1 and T1, so that R1 square plus T1 square, you can consider 1 if they are lossless. This can be considered R2 square plus T2 square, that can be lost. That means 2 coupling point. I am launching here. What happens? The resonant wavelength will store here, that will be missing here. But when it is stored, if it sees that another waveguide is coupled neighboring bus waveguide, then that resonant wavelength will be dropped here. So, if I have a broadband lambda, I am launching here. In this here, what I will see? Here I will see that this is lambda, a certain wavelength which is resonant, that will be missing in the transmission. Maybe regularly it will be a phasor, it will be missing here. But the wavelength which were missed here, that is stored inside the ring, but that stored energy can be taken out a bit here. So, in here in this output, what you will see? You will see exactly here I can plot. So, I can get something at this point, maybe you can get a little bit high, and here you can get a little bit high, and here you can get a little bit high. So, you can get that wavelength information. So, this is a very, very important device in add drop configuration, ring resonator in add drop configurations. We will see that this type of device not only used for a wavelength dropping add drop configuration, just a particular channel you can drop. Not only that, you can use this one as a so called modulator, multiplexer, demultiplexer, and normally nowadays all the on chip transceiver circuit, silicon photonics transceiver circuit, they are actually designed with microring resonators. Okay. So, we will discuss that in future, but at this point of time we will just try to understand this type of device from the knowledge of this simple microring resonator, which is actually called all pass configuration. When one bus waveguide ring, that is called all pass configuration, that means everything passing through this bus waveguide only, that is why it is called all pass. So, whatever things either it is storing or it is passing here, that is why it is called all pass. But in this case everything actually it is not passed, you have the drop port, something you can drop here. So, this is called all pass and this is called add drop. Why it is add? It can drop. Add means if you again that whatever the wavelength you are dropping here, that wavelength if you launch here, that will again couple to this ring and you can couple back here. So, you can add also. So, I have one input port, another input, second input port, one output port, another output port. So, two input ports, two output port, that is how add drop configuration we design. So, in this case how we can define what would be the bandwidth, full width maxima at resonance in terms of lambda, in terms of Q value, what would be the Q value, whether it will be increased or decreased, finesse, how you can modify this one. So, remember that in this case you have only one R1 T1 and no other things are there, but here in this case you have additional things. How to deal with it? So, here are some pictures. If say this is something bus waveguide here, this one, this is your bus waveguide, this fabricated device in our lab actually. So, you see this is the racetrack waveguide, something like this it is designed, and this two waveguides are coupled. So, light you launch here, it will couple, and one half it is shown here because you could zoom and see the waveguide things. And another add drop configuration we have taken from literature. That is a 3D view, little bit tilted, sample is little bit tilted, and scanning electron microscopic image. If you see, this is a 5 micron bending radius and little bit of flat portion racetrack design it is kept, so that you can couple light and couple out here. So, these are the design, but that is the fabricated device, how it will be, it is looking like after fabrication and for different type of applications. But our intention is now to find out equivalent formula for delta nu FWHM, delta lambda FWHM, Q value and finesse when the ring resonator is in add drop configuration. So, it is very easy. From here you can directly derive the expression for add drop configuration. How it is? Let us try to see. What you do? Earlier you have R1 and T1 here. That is why you are getting everywhere R1 and A you are getting, but A is what? A is round trip loss. A is round trip loss. Okay. So, if it is round trip loss is A, that means if I just consider I by AO, AI by AO equal to e to the power minus alpha L. If I just forget about the phase, that much is the round trip loss, right. So, A is, that means ratio AI to AO ratio is the A factor I will be getting, that is the A. Now, that means transmission coefficient, transmission, whatever transmission through this total ring. Now, in this transmission path you have additional coupler is there, where the transmission this will give you R2. That means you used to get A, now instead of A you will be getting AR2, because you have another coupler. Your loss factor is not A anymore, your loss factor is converted into AR2 because of the presence of the second waveguide. R2 is coming up path, that means maybe 90% is coming back, 10% may be going there, it can happen. So, that means earlier I was getting 99%, now not 99%, even I am losing something here. That is why new AR will be AR2, what was original A and R2, and originally instead of R I will have a R1. So, these expressions you can directly use for add drop multiplexer, just putting R equal to R1 and A equal to AR2. Wherever A is there you just put AR2, and wherever R is there you put R1. Then you can convert all this expression for actually add drop configuration. You see, for delta nu FR C1 minus RA, R I am putting R1, A I am putting R2A, and RA, R1 and A equal to R2A. Similarly, delta lambda 1 minus RA, R means R1, A means R2A, lambda R, and this pi ng L R1 R2A. Q value, you see, Q lambda R equal to pi ng, L is there, and square root of RA, R1 R2A, and RA R1 R2A. So, just you put R1, because originally it was R here, that is why all this coming R. Now, that place we have changed to R1 T1. So, R will be converted into R1, and A, because of the presence of second one, A is no more A, you have, it is modified to AR2. So, you just modify that one, then you get the direct equation. So, whatever once you solve, you could derive, we have derived already how to get all these expressions, figure of merits, just to convert, just to use them for add drop multiplexer, of course, you can find easily. So, that means only you need to design your directional coupler here for a desired R2T2, for a desired R1T1, and perimeter you design for a particular resonance wavelength you want to store or you want to drop, then it is fine, absolutely fine. Okay. Now, we want to show some experimental result as I promised. So, you see here is shown one ring resonator, this is the ring resonator. It is about, it is 100 micrometer, you see this is the scale. SEM image, it has been shown input grating coupler. This is grating coupler. We have discussed earlier, grating coupler is used just to couple light into the waveguide. So, you can bring fiber here, if you launch here, light will pass through the bus waveguide and you can take here. And this is the ring fabricated where you can expect some storage things. Energy will be stored, power will be stored at resonance. And that transmission characteristics we know how it will be looking like at resonance and what is the transmission. This is all pass configuration, one input, one output. Everything will be passed through that output only. That is why it is all pass configuration. So, this is called all pass configuration. Other one is add drop configuration. Okay. And here how we characterize, you see, this is the fiber coming, you see here, this is the fiber coming and this is your sample, and fiber is actually vertically about 10 degree. This grating is defined vertical coupling purpose, 10 degree inclination it is done. So, the grating coupler is designed. We have learned earlier already how the grating coupler need to be designed. Fiber is coming and you are taking out. Sample is this one. So, this is your characteristics result. You see, we have shown here two curve. You see one red curve. Red curve is one more additional waveguide structure is there as a reference where ring is not there. Just you launch grating coupler and grating coupler just to see what is the wavelength dependency in coupling grating coupler and what is the loss in straight waveguide, you can find out. So, you just normalize with a certain power, then you see that this you get this red curve here. Okay, red curve means wavelength, this is your wavelength dependent transmission you are seeing here in dBm scale. So, whatever transmission you are getting, you convert into milliwatt and then you take log 10 and log to the base 10 and convert milliwatt and you take log value, that is actually dBm. So, you get this one, and in the straight waveguide you see you do not see any resonances, but when you are launching here you see it is following same path, but at the same time some wavelengths if you see those are resonant wavelengths, those are missing in the output and they are having different extinction also. They are extinguished for different value. You see some resonances are extinguished very large up to 65 dBm and some of them very little. What is the reason? Because at resonance wavelength you see the transmission equal to R minus A square divided by 1 minus AR square. That means beta L equal to 2 m pi. You just put 2 m pi, then you get this result. But if you see R is what? It is the self coupling coefficient R and A is the round trip loss. So, carefully you look, if somehow at some wavelength if R equal to A, transmission at resonance will be 0. So, when R equal to A, the transmission output here at resonance wavelength will be getting absolutely minimum. You see all the resonance spectrum here which is missing in the transmission, a particular wavelength you see resonant wavelength, it is minimum at the output. So, that is happening because that is where you are getting R equal to A. So, that particular condition we can call it as a critically coupled. So, when you have a ring resonator and you have a bus waveguide and this is going R and this is going your T. Now, if R value is exactly equal to the round trip loss factor, then your transmission throughput happens to be 0. Here still you are getting little bit, that may be noise level. So, you can get 0, that is actually critical coupling. And right side if you go, that means this R value somehow it is greater than the round trip loss, and that is why your extinction is dropping. So, R is greater than A, your transmission will be reducing, you are increasing, transmission will be increasing, and R less than A, because it is a square value, that will also be reducing. So, that means I can say that this R is a function of lambda. Of course, A can be a function of lambda, but most of the time this round trip loss, waveguide loss is not a function of lambda, rather this R, this coupling coefficient of the directional coupler, that is actually function of wavelength. That is the reason as a function of wavelength you see extinction is different for all the resonance wavelength. So, that actually following this one. If you can design your directional coupler is actually wavelength independent directional coupler, then you would see all the resonances would be, extinction would be at the same level. Okay. So, if you just little bit expand this one of the resonance if you see exactly at the critical wavelength around 1550 something like that, one resonance you just pick, you zoom into a resonance wavelength, one of this resonance wavelength you zoom in, then you see how it is coming down and then going up. And you can find out maxima to minima 3 dB down, then you can get 3 dB bandwidth experimentally, 3 dB bandwidth in all pass configuration. Once you know 3 dB bandwidth, you know delta lambda FWHM and you know the resonance, then you can find the Q value. Q value is the lambda by delta lambda, that is what we have shown earlier. Okay. Now, we can actually find that I can calculate FSR, that means free spectral range between successive, that means wavelength separation between successive resonances. So, I know that this free spectral range is lambda square by NGL perimeter length. If I experimentally get the FSR and I know L and I know resonance wavelength, then I can find out group index. So, that is how you see as a function of wavelength I can find group index is also changing. That means Ng is also a function of lambda, group index of the waveguide, that is also function of lambda. That can be also, you can extract how is the waveguide you have designed, whether that is a group index is also dispersive or not, you can find out. And from group index also you can model what is the effective index, experimental you can extract what is the effective index. So, you just as a function of lambda you just calculate FSR, that means separation between two resonant wavelength, that is actually free spectral range, that is actually FSR, this plots all you have calculated, and once you know FSR you can find out Ng. So, group index as well as free spectral range you can extract from the experimental result. Okay. So, then once you know all these R value everything 3 dB bandwidth and lambda R, you can just see what is the quality factor. All the resonances you can find out the quality factor actually. You see towards the 1520 to 1600 nanometer we have the data, and initially Q value are low, low means it is about 3 into 10 to the power 4, 30,000 or so, and then as you go for longer wavelength in this region, so this is around critical wavelength. So, around critical wavelength Q value is about 30,000, as you go then you can go up to 80,000. So, some of the ring resonator we have developed, that is actually Q value is more than 10 to the power 5, that means 1 lakh or so. Okay. So, this is how the ring resonator we can design, we can get whatever the desired FSR, we can actually design whatever the Q value required, Q value actually highly dependent on what is the waveguide loss, what is the perimeter length, volume of the cavity, etc. And depending on that, we can think of various type of applications. And this ring resonator actually is heavily used for photonic integrated circuit. Two devices, that is Mach Zehnder interferometer and ring resonator, they are heavily used, and both of them are actually designed with directional coupler. So, we have discussed this microring resonator, Mach Zehnder interferometer, and maybe probably one more lecture I will spend to understand distributed Bragg reflector. That is also another important device for photonic integrated circuit. Then we can go for more complex design of different type of functions, like a reconfigurable filter, reconfigurable delay lines, all those type of things, how can be designed using these fundamental building blocks, that will be discussed. With this I stop today. Thank you very much.